Top 10 Theories about Dark Energy. Our knowledge of the cosmos and how it functions has grown immensely throughout time. We take pride in being the most intelligent species on Earth and, as of this point, the most powerful species in the entire cosmos. However, the knowledge we have about the structure of our universe comes from the little portion of 4% regular, everyday matter that we can observe, measure, and examine. The remaining 96% is dark material. The darkness is a result of our ignorance of it, and because physicists tend to lack creativity in the naming department. Approximately 68% of that 96% is dark energy. As a result, it is the biggest and currently most enigmatic part of the universe. Numerous researchers are trying to understand this enigmatic energy that appears to direct how our cosmos generates enormous structures. Our cosmos would eventually experience a big crunch, a gravity-dominated catastrophe in which the universe quickly collapses into itself if dark energy didn't exist. Therefore, even though we don't fully understand dark energy, we should be grateful that it exists. Here are the top 10 hypotheses on dark energy and what each one can reveal about the future of the cosmos. 10. It is a space-related property. The idea behind this hypothesis comes from Einstein's theory of gravitation, specifically from the idea that empty space can have its own energy, which is known as the cosmological constant. Einstein also thought that space could be produced out of nothing, and that as more space is made, more energy can be stored therein. This would explain the universe's observed rapid expansion. This kind of universe would grow endlessly until every object was so far off from every other object that it would all collapse into a chilly blackness. 9. Principle of everything. Many astronomers think it is pointless to look for dark energy. They argue instead that the issue of dark energy would be resolved by accident if the elusive theory of everything, not the Stephen Hawking film, were to be discovered. From extremely large objects to incredibly microscopic ones, this theory ought to be able to describe how they behave. We currently distinguish between large-scale theories, like the theory of gravity, and small-scale theories when describing how the cosmos functions, like quantum mechanics. Although finding this theory has shown to be unachievable for even the best brains in physics, solving the problem of dark energy in this manner is logically sound. When one approaches the quantum level, the conventional laws of physics appear to break down. But alas, the hunt continues. 8. A new fundamental force is produced. Gravity, electromagnetism, the weak force, and the strong force are the four known fundamental forces, and each operates in a certain range. Others set off the motions of planets and the birth of galaxies, while some simply have an impact on atomic-scale objects. According to this version of dark energy, a fundamental force that operates on gigantic sizes and can only be seen when the cosmos reaches a particular size still exists. It would function to counteract gravity and so draw cosmic objects apart from one another. Scientists contend that since we haven't yet experienced this force in our daily lives and measurements done on Earth are unaffected by it because it operates on such a vast scale. It's unclear whether this army would be a temporary or permanent one. However, depending on this, the universe would either continue to expand indefinitely and become cold, or it would continue to expand and contract occasionally for the rest of time. 7. The problem with Einstein's theory of gravity. Try informing one of the greatest physicists that his, perhaps, most well-known hypothesis is incorrect. Yikes. Everybody in the universe is attracted to every other body, according to Einstein's theory of relativity, with the intensity of that attraction entirely being determined by the masses of the objects and the distance between their centers. Some physicists, however, have contended that this hypothesis might be false and have started creating new gravity theories to explain dark energy. According to these beliefs, the effects of gravity on a vast scale are reversed, causing objects to resist one another. These ideas would explain why the universe is expanding, despite the lack of strong experimental support, because Einstein's theory of gravity has so far served us well. With these new gravitational theories, our universe would experience fast expansion followed by a return to chilly darkness. 6. Timing dilation. You have probably heard of time dilation if you have ever seen the movie Interstellar. It is a phenomenon that happens when time slows down for objects moving almost as quickly as light. The twin paradox, in which one twin travels aboard a spaceship that approaches the speed of light while his brother stays on Earth, illustrates the same concept. The twin on Earth is considerably older than his astronaut sibling when they reunite after years apart. According to a recent research by University of Georgia professor Edward Kiprios, only the moving object itself experiences time dilation. Typically, the effects are also felt by the person seeing the rapidly moving object. This would imply that time passed more quickly in the past. Since the apparent expansion of the universe would only be a mistake in calculating distances that have been impacted by time dilation, the need for a repelling force or material is eliminated. If this hypothesis is correct, it would not only be in conflict with another of Einstein's well-known theories, his theory of special relativity, but it would also indicate that the Hubble constant's effects would cause the universe to continue expanding. 5. A strange new particle. It has been known for millennia that there are particles and fields. We are aware that an electron generates an electric field, and more recently, the graviton, the force particle of gravity, has been linked to the gravitational field. The assumption that a specific field's energy must be conveyed via its force particle rather than by the field itself is accepted by particle physicists and theorists. Dark matter, which makes up the remaining 27% of the cosmos, can be translated to dark energy, which acts as its force particle. This theory looks tenable, especially in light of the graviton's unobservability as a force particle. We have not yet been able to measure any of the characteristics linked to dark energy or dark matter, thus there is little evidence to back up this notion. For F.R., theories serve as representations of the universe's current curvature, with curvature denoted as r. Researchers at the University of Chicago demonstrated in 2007 that for a given value of r, a universe model can be developed in which dark energy is not required to explain the universe's expansion. This kind of universe bends itself in a way that reduces its general curvature and generates an extra gravitational pull that, depending on a combination of circumstances, can either attract or repel objects. According to the researchers at the University of Chicago, for this hypothesis to be true, the extra force must vanish where gravity is reasonably strong, for instance, on the scale of planets and galaxies, and must only manifest itself at the biggest scales. In an effort to determine whether the F.R. theory is an accurate representation of our cosmos, a group of astronomers from Peking University have started measuring clusters. 3. The anthropic principle and multiple universes. The prediction of the real value of dark energy is one of contemporary physics' biggest mistakes. Physics researchers estimated a number that is almost 10,120 times larger than what quantum theory predicts, which is extraordinarily small. The cosmological constant, shown as atom 10 on this list, is the measured amount of dark energy. The anthropic principle, which holds that fundamental physical constants like the gravitational constant and the speed of light are just right for supporting life in our specific universe but may have different values in other universes, enters the picture at this point. It does not seem unlikely that our world just so happens to be the one with the right amount of dark energy to support the emergence of life in an endless number of parallel universes. 2. Virtual particles. It's strange, quantum mechanics. It enables for phenomena to appear and disappear, appending every physics principle we learned in high school. We murmured, matter cannot be formed or destroyed. This theory makes use of the concept of virtual particles, which are tiny pieces of matter that only briefly appear before dissipating. Because matter is transformed into energy when these particles vanish, the continual arrival and disappearance of particles releases energy. According to physicists, this is how space itself may accumulate enough steady energy to provide the negative pressure that propels the universe's expansion. If this hypothesis is correct, the energy that space acquires from these hypothetical particles might be the enigmatic dark energy, and our universe would continue to grow as long as this process persists. 1. Quintessence. The sheer quantity of theories on this list demonstrates how little we still know about 2/3 of the cosmos. Each theory has so far had a significant impact on the future of the cosmos or on poor Einstein. Understanding dark energy may pave the way for the development of a brand new field of physics or fundamentally alter those that already exist. Because of this, a substantial number of physicists and astronomers today doubt the existence of this dark stuff that controls the expansion of our universe. The most bizarre dark energy theory is, by far, this one. A world filled with an energy fluid is one that is dominated by quintessence. Some physicists prefer the term phantom energy to describe this energy. It is predicated on the notion that quintessence changes with space and time and that its energy density rises with time. This cosmos would have a catastrophic end known as a Big Rip, again, with the very literal nomenclature, in which the universe would actually burst because the speed at which atoms are being ripped apart and stretched is too great for them to keep up with. Everything visible and invisible would be destroyed. The end of the cosmos would be catastrophic. That's for now. We appreciate you for being here. View more our channel videos.